Worked example 20. True, reactive and apparent power and power factor. A single phase load has a power factor of 0.850 and draws a current of 10 amps with a supply voltage of 230 volts. Calculate each of the following: the true power, the reactive power, the apparent power. In order to calculate true power, we're going to use the formula P equals IV cos theta. And because it's the AC variant, we need to make sure we're putting that cos theta in there. Now, the bit that students often get confused about is cos theta is equal to power factor. So the two are fully interchangeable terms. Students often end up thinking they need to substitute in the theta and things like that. No, they don't. They can just basically substitute the whole of cos theta for the power factor. So our true power total is going to be our current of 10 amps multiplied by our voltage of 230 volts multiplied by our power factor, or cos theta, of 0.850. And that gives us a total power of 1,955 watts, or 1.96 kilowatts. For part B, to calculate the reactive power, Q, we're going to need to find out our phase angle first, so that we can use the formula IV sine theta. Theta is equal to cos inverse of the power factor, so theta becomes cos inverse 0.850, which gives us a phase angle of 31.79 degrees. We can use this now in our formula up here to calculate our reactive power. So Q is equal to 10 times 230 times sine of 31.79 degrees, and that gives us a total reactive power of 1,211.66 volt amps reactive, or 1.21 kVAR. Finally, total apparent power is S, and that is equal to I times V, which is 10 times 230, which gives us a total apparent power of 2,300 volt amps, or 2.3 kVA. An RLC circuit with an impedance of Z total is 50 at an angle of 30 ohms degrees, is connected to a 50 Hz 120 volt supply. Taking the supply voltage as reference, determine each of the following: the power factor of the circuit to 3 decimal places, the supply current, and the total apparent power. So our power factor is equal to cos theta, and we know the phase angle of the circuit because we're told it in the impedance here of 30 degrees. So we actually know that theta is 30 degrees, so we can say that power factor is equal to cos 30, and when we do that we end up getting 0.866 to 3 decimal places. There are no units for the power factor because it's a ratio, so we just leave it as 0.866. In part B, we're asked to work out the supply current, and we're asked to take the supply voltage as reference. So in that case, our IS is going to be Vs over Zt. Now bear in mind these are vectors, so we have to treat them as such. So we've got a voltage of 120 at an angle of 0 divided by an impedance total of 50 at an angle of 30. So just reminder, when we're doing complex division like this, we divide the magnitudes and we subtract the angles. So we have 120 divided by 50, which gives us 2.4 at an angle of 0 minus 30, which is minus 30 degrees amps. For part C, our total apparent power S is equal to our current of 2.4 multiplied by our voltage of 120. In this case, that gives us 288 volt amps. Question 3, a 3 kilowatt motor with a power factor of 0.0850 is connected to a single phase supply of 230 volts, 50 Hertz. And we're asked to determine, first of all, A, the current supply to the load, B, the phase shift caused by the motor to 1 decimal place, and C, the apparent power of the motor. So to determine our supply current, we've got the voltage, but we don't have the impedance, so we need to go from a different angle. And what we could do is we can say, well, power is IV cos theta, and we also know that that equals IV power factor. So we could rearrange this to get our I, which is our supply current, being equal to the power divided by the voltage times power factor. And that would give us 3000 divided by our voltage of 230 multiplied by our power factor of 0.850, and that gives us a supply current of 15.35 amps. For part B, we're asked to work out the phase shift, the phase angle, and that is a straightforward one of our phase angle is equal to cos inverse the power factor, so cos inverse of 0.850, and that gives us 31.8 degrees. For part C, we're asked to work out the apparent power S, which equals IV. In this case, that is 15.35 multiplied by our voltage of 230, and that gives us a total apparent power of 3530.5 volt amps, or 3.53 kilovolt amps.